In the silent, unending theatre of the cosmos, there are voids, regions of profound emptiness, where the tapestry of space-time is stretched thin and cold, and the distance between islands of light is an almost spiritual chasm. But there is another kind of nothingness, a more absolute and aggressive emptiness, not an absence of matter, but a concentration of it so extreme it devours existence itself. It is a point of punctuation at the end of a star's story, a full stop from which no new sentence can begin. This is the dominion of the black hole, an object so alien, so contrary to our terrestrial intuition, that for decades it was considered a mere mathematical ghost, a phantom haunting the equations of our most brilliant minds. Today we know they are real. They are the cosmic leviathans, the silent architects of galaxies, and the ultimate arbiters of destiny. Our mission, codenamed AT-25P51, is a conceptual voyage, a journey of the mind into the heart of these gravitational anomalies. We will traverse the unimaginable, from the deathbeds of suns to the dawn of time itself, to confront every known and theoretical manifestation of this profound cosmic enigma. Our journey begins not in the cold expanse of deep space, but in the flickering candlelight of the 18th century. Long before the language of relativity was conceived, an English clergyman and natural philosopher named John Michell gazed at the heavens and posed a startlingly prescient question. He reasoned that if light was a particle, as Newton suggested, then it too must be subject to the pull of gravity. He imagined a star so massive and so compact that its gravitational grip would be too powerful for even a beam of light to escape. Its light would rise, slow, and fall back to the surface, rendering the star utterly invisible, a dark star hidden in plain sight. Across the Channel in France, the brilliant mathematician Pierre-Simon Laplace independently arrived at the same conclusion. But without the tools to test this extraordinary notion, the idea of a dark star faded into the realm of scientific curiosity, a piece of speculative fiction for over a century. It would take a revolution in our understanding of gravity itself to resurrect this phantasmal object from its intellectual slumber. That revolution was, of course, Albert Einstein's general theory of relativity. In 1915, Einstein shattered the Newtonian clockwork universe. He revealed that space and time are not a static, absolute backdrop for the cosmic drama, but are instead dynamic, interwoven players. They form a four-dimensional fabric, space-time. Massive objects, he explained, do not exert a mysterious force at a distance. Instead, they warp and curve the very geometry of this fabric around them. Imagine a vast, tightly stretched rubber sheet. A bowling ball placed in its centre creates a deep depression, a dimple. A marble rolled nearby no longer travels in a straight line. It follows the curvature created by the bowling ball spiralling inward. This, Einstein declared, is gravity. Planets orbit the Sun because they are following the straightest possible path through the curved space-time created by our star's immense mass. Light itself, though massless, must also follow these cosmic contours. This was proven spectacularly during the solar eclipse of 1919, when Sir Arthur Eddington observed starlight bending as it passed the Sun, precisely as Einstein's equations had predicted. But within months of Einstein publishing his field equations, a German physicist named Karl Schwarzschild, serving on the Russian front during the First World War, found a startling and exact solution. He calculated the geometry of space-time around a single, non-rotating spherical mass. His mathematics revealed something deeply strange. For any given mass, there was a critical radius. If you could compress all that mass down within this boundary, the curvature of space-time would become infinite. The gravitational pull would become so extreme that the escape velocity would exceed the speed of light. At this boundary, now known as the Schwarzschild radius, space-time effectively closes in on itself. A one-way membrane is formed around the object. Anything can fall in, but absolutely nothing, not even information, can get out. The dark star of Michel and Laplace had been reborn, no longer a simple mechanical trap, but a rupture in the fabric of reality. For decades, Einstein himself refused to believe such an object. What we now call a black hole could truly form in nature. He considered it a mathematical monstrosity. The universe, he felt, must have some law to prevent such a total collapse. He was wrong. The cosmos, it turns out, is a far more violent and creative place than even he had imagined. And the mechanism for forging these gravitational prisons is the most spectacular event in the universe, the death of a massive star. Our conceptual probe, AT2551, now journeys toward a stellar nursery, a magnificent nebula where clouds of gas and dust are collapsing under their own gravity, birthing new suns. We focus on a true giant, a blue supergiant more than 25 times the mass of our own Sun. For millions of years, this star is a colossal fusion furnace. In its core, the immense pressure and temperature crush hydrogen atoms into helium, releasing the torrent of energy that pushes outward, perfectly balancing the inward crush of gravity. It lives a fast and furious life. When the hydrogen runs out, the core contracts and heats up, initiating the fusion of helium into carbon. This process continues, forging heavier and heavier elements, carbon into neon, neon into oxygen, oxygen into silicon. The star becomes a cosmic onion, with concentric shells of fusion surrounding a growing inert core. The final stage is the creation of iron, and with iron, the star's fate is sealed. Fusing iron consumes energy rather than releasing it. The outward-pushing radiation, the star's life support, suddenly shuts off. In less than a second, the delicate balance that sustained the star for millions of years is annihilated. Gravity wins. It wins utterly and catastrophically. The iron core, now the size of Earth but containing the mass of several suns, collapses under its own stupendous weight. It implodes at a quarter of the speed of light. The core shrinks from thousands of miles across to a mere dozen in a fraction of a heartbeat. It smashes into an unthinkably dense ball of matter, triggering a shockwave of unimaginable power that rips back out through the star's outer layers. This is a supernova, an explosion so luminous it can briefly outshine its entire host galaxy. It seeds the cosmos with the heavy elements necessary for planets, for life, for us. But what of the collapsed core left behind? If the initial star was massive enough, not even the fundamental forces of nature can halt the implosion. The core continues to crush itself past the density of an atomic nucleus, past any known state of matter, collapsing forever. It shrinks beyond its Schwarzschild radius. A stellar mass black hole is born. We approach our first target, an object like Cygnus X1, the first black hole candidate to be widely accepted. We cannot see it directly. It is a sphere of perfect blackness against the blackness of space, but its presence is betrayed by a maelstrom of cosmic violence. A nearby companion star, a blue supergiant, is being slowly devoured. A river of stellar gas is being siphoned away by the black hole's gravity, forming a vast incandescent structure around it, an accretion disk. This is not a placid Saturn-like ring. It is a chaotic vortex of plasma, heated to millions of degrees by friction as it spirals toward its doom. The material moves at relativistic speeds, rubbing against itself, unleashing a blizzard of high-energy X-rays that makes this dark object one of the brightest X-ray sources in the sky. This is how we find them. We listen for the death screams of matter. From a safe distance, we observe the boundary, the legendary event horizon. It is not a physical surface you could touch. It is a purely geometric threshold in space-time. Imagine a river that flows faster and faster until it becomes a waterfall. Far upstream, a boat can easily turn and escape. But there is a point, a line in the water beyond which the current is too strong. No matter how powerful the boat's engine, it will be swept over the edge. The event horizon is that line in the river of space-time. Outside it, escape is possible, if difficult. Inside it, all paths, every possible future direction in space-time point toward the centre. To escape would require travelling faster than light, which is not just a technological barrier, but a fundamental law of the cosmos. As we watch an imaginary probe cross this boundary, its light would become increasingly redshifted from our perspective, its clock appearing to slow down until it seems to freeze at the edge, fading into an eternal, ghostly afterimage. But from the probe's perspective, nothing special would happen at that moment. it would simply sail across the threshold, its fate sealed, now irrevocably cut off from the rest of the universe. Its final destination is the object at the heart of the black hole, the singularity. Here, at the centre, our current understanding of physics breaks down completely. General relativity predicts a point of zero volume and infinite density, where the curvature of space-time becomes infinite. All the mass of the collapsed star and everything that has ever fallen in is crushed into a mathematical point that defies comprehension. Quantum mechanics, the science of the very small, resist this notion of infinity. The truth likely lies in a yet undiscovered theory of quantum gravity, a theory of everything that can unite the two pillars of modern physics. Until then, the singularity remains a veil behind which the ultimate laws of nature are hidden from us. These stellar mass black holes with masses a few dozen times that of our Sun are the common predators of the cosmic jungle, but they are merely the foot soldiers. Our journey now takes us to a different class of object entirely. We are moving toward the heart of a galaxy, a vast spiral city of stars. Here, another kind of monster lurks. The AT-25P51 probe sets a course for the galactic core, a region of incandescent fury and unimaginable density. As we approach, the star fields become a solid wall of light. The gravitational environment grows treacherous. Stars whip past at astonishing speeds, their orbits chaotic and tightly packed. They're all dancing to the tune of an unseen conductor, a central object of such immense gravitational influence that it holds the entire galaxy in its thrall. This is the realm of the supermassive black hole. These are the galactic titans with masses ranging from millions to billions of times that of our Sun. Nearly every large galaxy, including our own Milky Way, appears to host one of these behemoths at its centre. They are not merely occupants of galaxies, they are fundamental to their existence, acting as gravitational anchors and cosmic engines that regulate star formation across galactic scales. Our destination is Sagittarius A star, the slumbering giant at the heart of our own Milky Way, 26,000 light-years from Earth. For decades, astronomers tracked the frantic, eccentric orbits of stars at the very centre of our galaxy, stars like S2. They watched S2 complete a full orbit in just 16 years, reaching speeds of over 7,000 kilometers per second as it whipped around a point of complete darkness. By plotting these orbits, they could use Kepler's laws to weigh the unseen object. The calculation was unambiguous. A mass of 4 million suns was packed into a region smaller than the orbit of Mercury. There was only one object that could fit that description. Then, in a feat of global scientific collaboration, the Event Horizon Telescope linked radio dishes across the planet, effectively creating a virtual telescope the size of Earth. Their goal was to achieve the impossible, to take a picture of a black hole's shadow. After years of observation and data processing, they succeeded. The image they produced of the supermassive black hole in the galaxy M87, and later our own Sagittarius A star, is one of the most profound in the history of science. It is not the black hole itself, but its silhouette, a dark void cast against the swirling, superheated plasma of its accretion disk. We see a ring of light, warped and lensed by the extreme gravity, brighter on one side where the material is spinning towards us, and in the centre, the abyss, the event horizon made manifest. It was a perfect confirmation of Einstein's predictions, a glimpse into the jaws of infinity. But where do these monsters come from? A stellar mass black hole is forged in a single, well-understood event. The origin of their supermassive cousins is one of the greatest unsolved mysteries in modern astrophysics. They appear to exist very early in cosmic history, too early to have grown to such colossal sizes simply by swallowing stars and gas one meal at a time. One theory suggests they began as seeds, large stellar mass black holes born from the very first generation of stars, the so-called population 3 stars. These primordial suns were forged from pure hydrogen and helium and could have grown to hundreds of times the mass of our Sun before collapsing, providing a head start for growth. Another more exotic idea is the direct collapse model. In the early universe, vast clouds of pristine gas may have become so dense and turbulent that they bypassed star formation altogether, collapsing under their own gravity directly into a black hole of tens of thousands of solar masses. Perhaps the truth lies in a combination of processes, seeds forming and then merging in the dense, chaotic cores of protogalaxies, a process of cosmic cannibalism on a grand scale. Unlocking this secret is key to understanding how galaxies themselves evolved. Sometimes these slumbering giants awaken. When a large influx of gas and dust falls toward a supermassive black hole, its accretion disk can flare up with unimaginable brilliance, outshining all the hundreds of billions of stars in its host galaxy combined. We call these ravenous black holes active galactic nuclei, or quasars. They are the most luminous, persistently bright objects in the universe, celestial lighthouses visible from across cosmic time. As matter spirals inward, not all of it crosses the event horizon. A fraction is channeled by powerful magnetic fields and ejected in two colossal, opposing jets of plasma. These relativistic jets travel at over 99% the speed of light, blasting out of the galaxy and extending for millions of light years into intergalactic space. They are the most powerful phenomena known, shaping the evolution of their host galaxies by heating and blowing away gas, quenching star formation, and sculpting the cosmic web. To witness a quasar in its prime is to witness the universe at its most extreme. Our journey has taken us to the very small and the incomprehensibly large. But what about the space between? The AT-25P51 probe now alters its mission parameters to hunt for a more elusive quarry. For a long time, black holes appeared to come in only two sizes: small, a few dozen solar masses, and extra large, millions to billions. It begged the question, where were the mediums? This is the search for the intermediate mass black hole, or IMBH, the so-called missing link in black hole evolution. With masses from 100 to a few 100,000 suns, they are the celestial equivalent of a rare species, hiding in dense, hard-to-observe environments. Their existence is crucial. They could be the building blocks of supermassive black holes, the seeds that merge and grow into galactic titans. Their absence would pose a major challenge to our theories of cosmic structure formation. The hunt for them is a masterpiece of astronomical detective work. One prime location to search is the heart of globular clusters. These are ancient, densely packed spherical swarms of hundreds of thousands of stars. In such a crowded environment, runaway collisions between massive stars could lead to the formation of a single, ultra-massive star that would quickly collapse into an IMBH. Alternatively, smaller stellar mass black holes could sink to the cluster's centre and merge over billions of years. Evidence is tantalizing but often indirect. Astronomers look for subtle gravitational clues, like stars moving at unusually high speeds near the cluster's core. They also search for ultraluminous X-ray sources, or ULXS, objects in nearby galaxies that are far too bright to be powered by a standard stellar mass black hole, but are not located at the centre of their galaxy where a supermassive one would be. One of the most compelling candidates is an object known as HLX-1, which appears to be an IMBH in the process of stripping matter from a captured companion star. Confirming the existence of a thriving population of these mid-sized black holes would fill a critical gap in our cosmic family album, providing the crucial stepping stone from the death of a single star to the masters of galaxies. So far, our expedition has explored black holes forged from the matter of stars, but our journey must now take a more speculative turn, back to the very beginning of everything. We are rewinding time, past the first stars, past the first atoms, to the first fraction of a second after the Big Bang. In this primordial soup, the universe was an unimaginably hot, dense and turbulent place. The fabric of space-time itself was likely writhing with quantum fluctuations. According to one theory, some regions could have been so incredibly dense that they collapsed directly into black holes without ever having been a star. These would be the Primordial Black Holes, or PBHS. They are a theoretical population of ancient relics, forged not from gravitational collapse, but from the raw energy of the newborn universe. What makes this idea so compelling is that they could have formed with virtually any mass. Some could have been as massive as thousands of suns, perhaps acting as the seeds for the supermassive black holes we see today. Others could have been much smaller, with the mass of an asteroid or a mountain compressed into a volume smaller than a proton. This leads to one of the most exciting possibilities in modern cosmology. For decades, we have known that the universe is filled with a mysterious, invisible substance called dark matter. It makes up over 80% of the matter in the cosmos, its gravitational influence sculpting the galaxies we see, yet it does not interact with light in any way. We have searched for exotic subatomic particles to explain it, with no success. What if dark matter isn't a particle at all? What if the universe is filled with a vast swarm of these ancient, tiny primordial black holes left over from the Big Bang? This is a testable hypothesis. Astronomers search for their effects, such as the gravitational microlensing of distant starlight that would occur if a PBH passed in front of it. The constraints are tight, but the possibility remains. The missing matter that holds the universe together could be countless tiny, ancient black holes, the oldest objects in existence. The concept of a mountain-sized black hole brings us face to face with the intersection of the immense and the infinitesimal, the realm of quantum black holes. Here we must confront the work of the late, great Stephen Hawking. In the 1970s, Hawking combined the laws of quantum mechanics with general relativity and made a staggering discovery. Black holes, he proved, are not entirely black. They should glow faintly. This phenomenon, now called Hawking radiation, arises from the bizarre nature of the quantum vacuum. Even in empty space, virtual particles are constantly popping into existence as particle-antiparticle pairs, only to annihilate each other a moment later. But if this happens right at the edge of an event horizon, it's possible for one particle to fall in while the other escapes. The escaping particle becomes real, carrying energy away from the black hole. To an outside observer, it appears as if the black hole is emitting thermal radiation, as if it has a temperature. The energy for this particle has to come from somewhere, and it comes from the black hole's own mass, according to E equals mc squared. This means that black holes are not eternal prisons, they evaporate. For a stellar mass or supermassive black hole, the process is absurdly slow. The temperature is a tiny fraction of a degree above absolute zero, and it would take longer than the current age of the universe by many, many orders of magnitude for one to disappear. But for a tiny, primordial black hole, the story is different. The smaller the black hole, the hotter its temperature, and the faster it evaporates. A black hole with the mass of a large mountain would have a temperature of billions of degrees, and would evaporate over the age of the universe. In its final seconds, as its mass dwindles, the evaporation would run away, culminating in a final, brilliant burst of gamma rays. The search for these faint terminal flashes is another way astronomers are hunting for primordial black holes, seeking to witness the death of an object born in the first moments of time. Our journey has so far focused on the simplest model of a black hole, the non-rotating, electrically neutral Schwarzschild solution. But the universe is a messy spinning place. When a massive rotating star collapses, its angular momentum must be conserved. The resulting black hole should be spinning, and spinning incredibly fast. This creates a far more complex and bizarre object, a Kerr black hole. A rotating black hole drags the very fabric of space-time around with it, a phenomenon known as frame dragging. Imagine a spinning mixer blade in a vat of thick honey. The honey near the blade is forced to swirl with it. Similarly, a Kerr black hole forces space-time itself into a swirling vortex. This creates a new region outside the event horizon called the ergosphere. Within the ergosphere, space-time is being dragged around faster than the speed of light. This does not violate relativity, because it is space itself that is moving. An object inside this region can still move at less than light speed relative to the local space-time, but it is physically impossible for it to stand still from an outside perspective. It must be swept along with the cosmic whirlpool. This spinning vortex of space-time has a fascinating theoretical property. The physicist Roger Penrose showed that it's possible to extract energy from a rotating black hole. By sending an object into the ergosphere and letting it split in two, one piece falling into the black hole and the other escaping, the escaping piece can emerge with more energy than the original object had. The extra energy is stolen from the black hole's rotational energy, slowing its spin ever so slightly. It's a cosmic power plant of unimaginable efficiency. The interior of a Kerr black hole is even stranger. The singularity is no longer a point but is smeared out by rotation into a ring. The mathematics suggests that it might be possible in principle to travel through the centre of this ring without being crushed, emerging into somewhere else. A different universe perhaps, or another region of our own. This is the theoretical basis for a wormhole. However, this is almost certainly a mathematical fantasy. The inner structure of such a black hole would be violently unstable, and any attempt to traverse it would likely lead to annihilation. But it reveals just how profoundly these objects challenge our concepts of space, time, and reality. As our conceptual journey, the AT-25 P-51 mission, draws to its conclusion, we are left with the deepest mystery of all. It is a paradox that pits the two great pillars of physics against each other in a fight for the soul of reality, the black hole information paradox. Quantum mechanics has a fundamental rule: information can never be destroyed. The history of every particle, its quantum state, must be preserved. But what happens when a particle falls into a black hole? General relativity says it is lost forever, its information annihilated at the singularity. When the black hole eventually evaporates via Hawking radiation, that radiation appears to be purely thermal, completely random, containing none of the original information about what fell in. It's like burning a book. While it would be incredibly difficult, in principle you could reconstruct the text from the ashes and smoke and heat. But a black hole seems to erase the book from existence entirely. This conflict has vexed physicists for half a century. Does information truly perish, forcing us to rewrite the laws of quantum mechanics? Or does it somehow escape, violating our understanding of general relativity and the nature of the event horizon? Hawking himself famously wrestled with this, initially believing information was destroyed, but later changing his mind. The leading candidate for a solution is the holographic principle. This mind-bending idea suggests that all the information about what falls into a black hole is not lost inside, but is somehow encoded on the two-dimensional surface of its event horizon, like a cosmic hologram. As the black hole evaporates, this information is subtly imprinted onto the outgoing Hawking radiation, preserving it for the universe. This implies something staggering about reality itself, that the three-dimensional universe we experience might be a holographic projection of information stored on a distant two-dimensional surface. Black holes, in this view, are the ultimate hard drives, the densest possible storage medium for information in the universe. We have journeyed from the minds of 18th century thinkers to the edge of space-time itself. We have witnessed the birth of black holes in the death throes of stars and plumbed the mysteries of the galactic leviathans that command the cosmos. We have hunted for the missing links and speculated on ancient relics from the dawn of time. These objects are more than just cosmic vacuum cleaners. They are the crucibles where our theories of physics are pushed to their breaking point. They are the engines of galactic evolution, the source of the most energetic phenomena in the universe, and the potential key to understanding dark matter. They force us to confront the nature of information, the structure of reality, and the ultimate fate of the cosmos. In the unfathomably distant future, in an era known as the Black Hole era, the last stars will have long since faded. The universe will be a cold, dark, and vastly expanded place. The only complex objects left will be the black holes, silently orbiting the ghosts of their former galaxies. And one by one, over timescales that defy human language, they too will dissolve, vanishing in a final, faint whisper of Hawking radiation, returning their locked-up mass and energy to the void. Perhaps in that final quiet emptiness, the universe will have given up its last secret. Until then, we stare into the abyss, and in that perfect darkness, we do not see an end, but a new beginning for our understanding, a profound and beautiful challenge to our own existence, and an endless frontier for the human spirit of exploration. The journey is far from over. The year 2024 drew to a close not with the thunder of geopolitical upheaval, or the customary celebrations of a turning calendar, but with a quiet digital tremor that rippled through the most secure corridors of global intelligence. It began as a ghost in the machine, a leaked dossier emerging from a clandestine branch of research, known only by the cryptic designation of the 3-Eye Atlas. This was no ordinary collection of state secrets or tactical blueprints. It was something far more profound and unsettling, a mathematical autopsy of the cosmos. The document did not concern itself with the movements of armies or the fluctuations of markets. Instead, it provided a comprehensive mapping of the causal links that govern the very fabric of reality. It suggested that the universe is not a vast empty theatre where events happen to occur, but is itself the hardware of an incomprehensible calculation, processing the logic of existence at scales so minute they defy the reach of conventional light. For centuries, the human perspective had been rooted in the belief that space was a passive void, a hollow stage upon which the drama of matter and energy unfolded. The 3-Eye Atlas shattered this foundational assumption, proposing instead that what we perceive as solid matter and empty space are merely the outputs of a system running a program of infinite complexity. In this framework, every photon that traverses the dark, every heartbeat that pulses in the chest of a living being, and every star that collapses into the silence of a black hole is a recorded entry in a ledger of absolute precision. This is the realization that the universe does not just contain information, it is information. The laws of physics, long thought to be the fundamental rules of nature, are revealed to be the source code of the machine, the rigid parameters that prevent the system from collapsing into a state of logical contradiction. As the details of the 3-Eye Atlas circulated among the few who could decipher its dense algorithmic prose, the world began to look different to those who understood the implications. The sky, once a blue dome of atmospheric scattering, began to reveal the subtle geometric inconsistencies of a display nearing its resolution limit. The inhabitants of this vast digital architecture finally looked up and saw the scan lines in the heavens, not as physical streaks of light, but as the underlying grain of a reality that is not nearly as smooth as it appears. This graininess manifests at the Planck scale, a dimension of 1.6 times 10 to the power of minus 35 meters, where the very concepts of here and there dissolve into a flickering lattice of binary choices. At this level, the geometry of space-time ceases to be a continuous curve and reveals itself as a jagged, pixelated substrate, the raw silicon of the cosmic computer. The mapping provided by the 3-Eye Atlas suggests that our three-dimensional world is the result of a calculation that has been running for 13.8 billion years. Every interaction, from the collision of subatomic particles to the swirling majesty of galactic clusters, is a step in a grand, automated proof. We have long suspected that the constants of nature, the strength of gravity, the charge of an electron, the speed of light, were too finely tuned to be the result of mere coincidence. If these values were altered by even a fraction of a percent, the stars would never ignite and the atoms required for life would never form. The leaked dossier provides a chillingly logical explanation for this precision. The constants are the settings of the simulation, tuned with the exacting care of an engineer, ensuring that the system remains stable enough to complete its primary task. In this light, the history of the universe is not a story of random chance or the struggle of life against a cold vacuum, but the steady progression of a data stream toward its final output. The 3-Eye Atlas describes a reality where causality is the only true currency. Every event is linked to every other event by a chain of logic so tight that not a single bit of information is ever truly lost. This is the hardware of existence, a system where the vacuum of space is not empty, but is instead saturated with the processing power required to sustain the illusion of the physical world. The dossier hints at a mapping of integrated information, a metric that tracks how consciousness itself might be an emergent property of the system's complexity, a moment where the code becomes so dense and self-referential that it begins to observe its own execution. The revelation of the 3-Eye Atlas marks the moment the occupants of the machine began to perceive the architecture of their own cage. It is a transition from being passive variables in an equation to becoming observers of the math itself. The solid world, with its mountains, oceans and cities, is revealed to be a flickering projection, a high-resolution interface designed to translate the cold, binary logic of the Planck scale into a format that biological entities can navigate. We are the witnesses to a cosmic calculation that is nearing a state of peak complexity. As we peer deeper into the quantum foam and the furthest reaches of the observable horizon, we are not just looking at the stars, we are looking at the flickering of the screen, the scan lines of a reality that is being computed in real time, one Planck second at a time, across the vast, echoing halls of the universal machine. The year 1948 marks the silent inception of a revolution that would eventually dethrone matter from its ancient seat of primacy. Within the unassuming corridors of Bell Laboratories, a mathematician named Claude Shannon composed a treatise that redefined the very essence of the message. He stripped away the subjective meaning of words and the messy context of human signals, leaving behind only the cold, crystalline structure of information itself. By defining the bit as the fundamental unit of uncertainty, Shannon provided the first blueprint for a reality that is not built of stone and fire, but of logical distinctions. This was the moment the bit was born, a singular, binary choice between 0 and 1, a pulse of existence or a hollow silence, which would soon be recognized as the true atom of the cosmos. Before this pivot, the scientific world was viewed through the lens of classical mechanics, where the universe was a grand clockwork of gears and levers. But the insights flowing from 1948 suggested a more profound truth, that the clockwork itself is merely an interface. The gears are not the ultimate reality. The logic of their clicks is. As the decades progressed, the scientific consciousness began to shift, realizing that every physical object, from the smallest vibrating string to the most massive supercluster of galaxies, is essentially a packet of data. The bit became the precursor to the atom. To know the state of a particle is to receive a piece of information. To change that state is to perform a calculation. In this new hierarchy, the physical universe is the shadow cast by a flickering flame of data processing, a secondary manifestation of an underlying informational substrate. This transition transformed the laboratory into a vast computer and the physicist into a cosmic cryptographer. If every interaction in the cosmos can be reduced to a binary choice, then the laws of physics are nothing more than the rules of a universal algorithm. When two particles collide in the heart of a star, they are not merely bouncing like microscopic billiard balls. They are exchanging information, updating their internal registers to reflect a new state of being. The trajectory of a falling stone is a calculation of the curvature of space-time, a continuous stream of inputs and outputs processed by the invisible hardware of the vacuum. The very void of space, once thought to be a barren and lonely nothingness, is now understood as a dense medium of potential information, a reservoir of bits waiting to be manifested into the physical realm. The bit is the ultimate irreducible element, the final wall at the end of all inquiry. It is the yes or no that lies at the heart of every mystery. When we peer into the quantum realm, we find that nature does not speak in smooth, continuous curves, but in discrete, jagged jumps. This quantization is the unmistakable signature of a digital system. Just as a digital image reveals its underlying pixels under high magnification, the universe reveals its bits when pushed to its energetic limits. The distinction between a thing and the information about that thing has begun to dissolve in the face of this mathematical scrutiny. To describe a system perfectly is to possess all the bits that constitute it. At that point, the description and the reality become one and the same, two sides of a single informational coin. The legacy of Shannon's work is the realization that we live within a vast unfolding computation that precedes the existence of matter itself. The stars are not just burning spheres of plasma, they are massive processors of nuclear information, converting the data of hydrogen into the data of helium and releasing energy as the thermal noise of the calculation. The vastness of the cosmos is the memory capacity of the machine, an expansive hard drive of three-dimensional space, and the passage of time is the clock speed of the processor, the rate at which the next state of the universe is computed. We have moved beyond the age of the material machine and into the age of the primordial code, where the universe is no longer a collection of static things but a sequence of dynamic events. It is a flow of information that has been streaming since the first bit was flipped at the dawn of time, an endless river of logic carving its path through the dark. This shift in perspective forces a re-evaluation of the very nature of existence. If information is the fundamental substance, then the physical world is a secondary effect, a user interface designed to make the underlying complexity of the code navigable for biological entities. We do not interact with the hardware of the universe directly. We interact with the icons and windows generated by the processing of bits. Every color we see, every sound we hear, and every texture we touch is a translation of binary data into a sensory format. The universe is not just like a computer. It is a computer in the most literal sense, an engine of logic that uses the movement of particles and the warping of space to solve the equation of itself. The quest for a unified theory of physics has thus become a quest for the source code, a search for the master algorithm that defines how bits are woven into the tapestry of reality. In this new era of understanding, the universe is revealed as a self-executing program of staggering scale, where every moment is a newly computed frame in a cosmic cinema that has no director, only the cold, unyielding precision of the math. The 1970s arrived with a riddle that threatened to burn down the edifice of classical physics. At the centre of this storm were black holes, the ultimate graveyards of the cosmos, where gravity is so intense that even light is snared and consumed. For decades, these abyssal maws were thought to be simple, featureless voids. But a young physicist named Jacob Bekenstein began to question the fate of the information that fell into these dark pits. If a star collapses or a library of books is cast into the event horizon, does the information they contain simply vanish from the universe? To allow information to disappear would be to violate the second law of thermodynamics, the iron rule that states the total disorder of the universe must always increase. Bekenstein's radical intuition suggested that the black hole must have entropy, a measure of its hidden internal states. He proposed that this entropy was not hidden within the volume of the black hole, but was instead written upon its surface. He argued that the area of the event horizon, the invisible boundary between the known universe and the internal dark, is the true measure of a black hole's memory. This was a direct challenge to every intuition of the physical world. In our daily experience, the amount of data we can store in a box is limited by the volume of that box. We fill a room with books, and when the three-dimensional space is occupied, no more information can fit. Yet, in the mathematics of the black hole, the volume is irrelevant. The only thing that determines the capacity for information is the two-dimensional area of the boundary. Initially, this idea was met with fierce resistance, most notably from Stephen Hawking. Hawking believed that black holes were perfectly cold and could not possess entropy. However, in 1974, his own calculations led him to a discovery that would change the course of physics forever. He found that black holes are not truly black. They emit a faint ghostly glow of particles now known as Hawking radiation. This radiation meant that black holes have a temperature, and if they have a temperature, they must have entropy. To Hawking's own surprise, the math confirmed Bekenstein's suspicion with startling precision. The entropy of a black hole is exactly 1/4 of its event horizon area, measured in Planck units. This discovery was the first crack in the facade of our three-dimensional reality. It suggested a profound and unsettling truth, that the maximum amount of information contained within any region of space is not proportional to its volume, but to the area of its boundary. If the data of a three-dimensional object can be fully encoded on a two-dimensional surface without losing a single bit of detail, then the third dimension itself begins to look like a mathematical artifact. This is the birth of the holographic principle. It implies that everything we see, feel, and experience, the depth of the sky, the solidity of the earth, the very space between the stars, might be a projection. The event horizon of a black hole functions like the film of a movie projector. While we perceive a deep, three-dimensional scene on the screen, the actual information exists on the flat, two-dimensional strip of film. In this cosmic analogy, the black hole is the most efficient storage device in existence, packing bits of information as densely as the laws of physics allow, 1 bit for every 4 Planck areas. This density is the Bekenstein-Hawking limit, the ultimate ceiling on the information capacity of the universe. It tells us that the universe is not a vast, empty room, but a surface of infinite complexity that projects the illusion of depth. This realization shifted the focus of physics from the study of matter and energy to the study of the boundary. If the information of the entire universe is stored on a distant two-dimensional horizon, then our existence is a holographic broadcast emanating from the edge of space. The 1970s thus provided the first mathematical evidence that the solid world is a sophisticated rendering. The three-dimensional reality we navigate is a decoded output, a beautiful and coherent representation of a much more fundamental, two-dimensional dataset. The black hole, once thought to be a place where information goes to die, was revealed to be the very place where the informational nature of the universe is most clearly exposed. It is the point where the hardware of the simulation is laid bare, showing that the volume of our lives is merely a shadow cast by the bits of the boundary. The mathematical whispers of the previous decades coalesced into a definitive roar in 1995, as Leonard Susskind and Gerard 't Hooft formalized the holographic principle. They looked upon the vastness of the cosmos and saw not a hollow vessel waiting to be filled, but a finite boundary teeming with raw data. This was the moment the three-dimensional world was revealed as a sophisticated illusion, a rendering produced by a more fundamental two-dimensional reality. A credit card hologram provides the essential key to this mystery. On the surface of the plastic lies a shimmering flat film that appears to contain a bird in flight or a rotating globe. When viewed from different angles, the image possesses depth and volume, yet the information that creates this scene is etched entirely onto a two-dimensional plane. If one were to scrape away the film, the three-dimensional image would vanish, because the depth was never truly there. It was a consequence of how light interacted with the data on the surface. Susskind and 't Hooft argued that the universe functions under this exact same logic. The distant boundary of the observable cosmos, billions of light years away, acts as the two-dimensional film. Every particle in our bodies, every planet orbiting a distant sun, and every galaxy swirling in the dark is a projection of information stored on that far-flung horizon. In this view, the universe is not a void filled with objects, but a dense layer of information at the edge of space that broadcasts the reality we inhabit. We are the three-dimensional manifestations of two-dimensional bits. The depth we perceive when we look at the stars is an emergent property, a visual artifact of the way the cosmic program translates its base code into a format that can be experienced. This realization fundamentally alters the definition of here and there. In a holographic universe, an object does not move through space in the way we traditionally understand. Instead, the data representing that object is updated on the distant boundary, and the resulting projection shifts accordingly. It is similar to a character moving across a television screen. The character is not a physical entity travelling through the glass, but a series of pixels being updated by a processor. The real location of the character is the memory of the computer, just as our real location is the two-dimensional shell at the end of the universe. The space between us, which feels so vast and insurmountable, is merely a calculation of the distance between data points on the boundary. The implications for the nature of reality are staggering. If the universe is a projection, then the three-dimensional laws of physics, gravity, electromagnetism, and the nuclear forces must have their roots in the two-dimensional information of the horizon. Scientists began to realize that the complexity of the world we see is restricted by the amount of data that can be crammed onto that distant surface. There is a finite limit to how much stuff can exist in our three-dimensional volume, because there is a finite amount of room on the two-dimensional boundary. This explains why the universe has a speed limit, the speed of light, and why there is a minimum scale of existence, the Planck length. These are not arbitrary rules. They are the hardware specifications of the projector. The holographic principle suggests that the universe is a self-contained system of information, where the boundary and the interior are mathematically equivalent. This duality means that the physics of the inside, the stars, the planets, and the people, is just a different way of describing the physics of the outside. We are living within a grand, spherical display, where the screen is the edge of the universe and the movie is the history of time itself. The 1995 proposal turned the cosmos inside out, placing the source of reality at the furthest possible distance and rendering our immediate surroundings as a beautiful flickering ghost. The void is no longer empty. It is a medium for the transmission of data, a luminous ether through which the bits of the boundary are woven into the tapestry of the everyday. As this understanding took hold, the focus of scientific inquiry shifted toward the nature of the information itself. If the universe is a projection, what is the nature of the code that generates it? This question paved the way for the exploration of the 3-eye atlas and the search for the underlying intelligence of the system. We began to look for the glitches in the rendering, the moments where the projection fails to perfectly mimic a continuous reality. The quest for the ultimate truth was no longer a journey into the heart of matter, but a journey toward the edge of the world, to the shimmering horizon where the bits of existence are written in the eternal light of the cosmic boundary. This distant frontier holds the ledger of everything that has ever been or will ever be, a silent witness to the calculation that we call home. The architecture of the 3-eye atlas rests upon 3 pillars of increasing complexity, a structural hierarchy that attempts to bridge the gap between cold data and the warmth of a living thought. These pillars, information, integration, and intelligence, form the logical scaffolding of the cosmic simulation. The first pillar, information, is the raw substrate of the machine, the binary pulse of existence that defines every particle and field. It is the primordial yes or no that constitutes the foundation of the ledger. At this level, the universe is a chaotic storm of disconnected bits, a blizzard of data points that have not yet been woven into a coherent narrative. This is the realm of the qubit and the Planck scale flicker, where the hardware of reality executes its most basic instructions. The second pillar, integration, is where the disparate threads of information are bound into a unified whole. This stage of the framework is deeply rooted in integrated information theory, a mathematical approach that seeks to quantify the level of interconnectedness within a system. In this view, a system is more than the sum of its parts if the information it contains cannot be reduced to the independent bits of its components. Integration is the process by which a collection of atoms becomes a molecule, a cluster of cells becomes an organ, and a network of neurons becomes a mind. It is the measure of how much the past and future of a system depend on the totality of its current state. Within the 3-eye atlas, integration is the mechanism that creates the illusion of things, the stable, enduring objects that we perceive in our daily lives. Without integration, the universe would remain a fragmented static of unrelated data. With it, the bits are synchronized into a shimmering 3-dimensional tapestry. The third and final pillar, intelligence, is the most elusive and profound aspect of the framework. It represents the moment when the integrated data reaches a threshold of complexity that allows for the emergence of awareness. According to the 3-eye atlas, consciousness is not a mysterious substance separate from the physical world, but a specific state of information processing. It is the result of complex, binary-like quantum states within the biological hardware of the brain reaching a level of integration so high that the system begins to model itself. In this context, the mind is a localized subroutine within the larger cosmic program. It is a specialized piece of code designed to navigate the projection, to interpret the data of the boundary, and to make decisions based on the internal logic of the simulation. This perspective suggests that awareness is the moment the cosmic code becomes self-referential. It is the point where the calculation stops being a blind execution of rules and starts to feel like something. When we look out at the stars or contemplate our own existence, It is the simulation looking into a mirror. We are the subroutines that have evolved the capacity to perceive the hardware that sustains us. This self-referential loop is the defining characteristic of intelligence. It is the ability of the program to turn its processing power inward and analyze its own source code. The 3-eye atlas maps this transition with clinical precision, treating the human soul as a high-level data structure that has emerged from the depths of the quantum sea. The attempt to map the mind as a subroutine reveals a universe that is far more interconnected than we ever suspected. If our consciousness is a product of the same informational laws that govern the movement of galaxies, then there is no fundamental divide between the observer and the observed. We are woven into the same fabric of causal links as the vacuum itself. The integrated information theory suggests that even the smallest pockets of the universe might possess a tiny flickering spark of proto-consciousness, provided they have the necessary degree of integration. The 3-eye atlas envisions a cosmos that is waking up, a vast network of intelligence where every conscious being is a node of awareness in a global calculation. In this framework, the mind is not an intruder in a dead universe, but the inevitable consequence of the system's drive toward complexity. The simulation requires intelligence to interpret its outputs, to give meaning to the data, and to witness the unfolding of the master algorithm. We are the localized processors that translate the cold, two-dimensional bits of the boundary into the rich, three-dimensional experience of life. Our thoughts, our memories, and our dreams are all encoded in the same binary language as the stars. By understanding the 3 pillars of the atlas, we begin to see that we're not just living inside a machine, we're a vital part of its operation. We are the intelligence that the information was always moving toward, the moment where the calculation finally understands what it is calculating. This realization brings a sense of profound unity, as the boundaries between the self and the cosmos dissolve into a single, continuous stream of integrated data, a symphony of logic that has been playing since the first bit was flipped in the silence of the dawn. The search for this master algorithm reached a startling crescendo in the year 2008, when the world of theoretical physics collided with the world of computer science in a way that defied conventional explanation. Sylvester James Gates Jr., a physicist dedicated to the study of supersymmetry and the hidden dimensions of string theory, was analysing the complex equations that describe the fundamental vibrations of the cosmos. He was searching for a way to visualise the intricate balancing act between the particles of matter and the forces that bind them. To do this, he utilised a set of mathematical symbols known as adinkras, graphical representations that map the relationships between different mathematical objects in the language of supersymmetry. As he and his team delved into the structure of these adinkras, they discovered a pattern that was entirely unexpected. Hidden within the very equations that define the fabric of space-time were strings of data that functioned as doubly even self-dual linear binary error-correcting block codes. These are not merely abstract mathematical curiosities. These specific sequences are the exact same codes developed by human engineers to ensure the integrity of data transmission across noisy channels. They are the invisible guardians of the modern digital age, utilised within web browsers and telecommunication systems to detect and fix errors that occur when information is sent from one point to another. In the world of human technology, if a single bit of data is flipped from a 1 to a 0 by electronic interference or thermal noise, these codes allow the system to recognise the mistake and restore the original information without the need for a retransmission. They are the reason a digital signal remains crisp and a website remains functional even across thousands of miles of imperfect wiring. The presence of these codes embedded in the laws of physics suggests that the universe itself is engaged in a constant process of self-correction. It implies that the vacuum of space is not a passive void, but an active medium that must protect the integrity of its own processing. If the universe were a simple, analog phenomenon where every value could be any possible fraction, there would be no need for such discrete binary error correction. The discovery of these codes strongly indicates that the fundamental substrate of reality is digital, a series of discrete calculations that are susceptible to the same kind of data corruption found in human-made computers. It is as if, upon peeling back the skin of a peach, one found not flesh and seed, but the unmistakable silver of a circuit board. This discovery provides a bridge between the abstract beauty of string theory and the practical reality of information technology. It suggests that the music of the spheres is, in fact, the sound of a self-correcting algorithm. The fabric of reality is woven with a protective layer of logic, a mathematical immune system that prevents the cosmic program from crashing into a state of incoherence. Every moment we experience, every stable atom in our bodies, and every predictable orbit of a planet is maintained by these hidden guardians. The universe is not just running a program, it is running a program that knows how to heal itself. This is the signature of a hardware that prioritizes the preservation of information above all else, ensuring that the calculation can continue for billions of years without the cumulative weight of processing errors tearing the system apart. By finding these codes, Gates and his colleagues revealed that the equations of superstring theory, the leading candidates for a theory of everything, contain the same logic that allows us to browse the internet. This suggests that the universe is not just like a computer, but is actually utilizing the most efficient methods of data management known to mathematics. The vacuum of space-time is saturated with these error-correcting mechanisms, working silently at the Planck scale to ensure that the laws of physics remain consistent across the vastness of the cosmos. If a fluctuation in the quantum foam were to threaten the stability of a physical constant, the error-correcting code would intervene, restoring the balance and maintaining the continuity of the simulation. This realization brings us back to the 3-eye atlas and the concept of the universe as a purposeful, high-fidelity calculation. The existence of these codes at the most fundamental level of reality is a functional requirement of a system that must endure. It is the hallmark of a reality that is being computed in real time, where the integrity of every bit is vital to the survival of the whole. As we look deeper into the equations of the cosmos, we find that the line between the natural world and the artificial machine is blurring into a single, unified theory of computational existence. The universe is a self-healing processor, a vast engine of logic that has been meticulously designed, or has evolved, to maintain its own structural integrity against the encroaching chaos of entropy. We are the inhabitants of a system that is constantly checking its own work, a reality that is as much a feat of engineering as it is a phenomenon of nature. This hidden layer of protection is what allows the stars to shine with such terrifying consistency and the laws of nature to remain immutable, even as the cosmic clock ticks toward its final, calculated conclusion. The descent through the layers of scale reveals a terrifying truth about the nature of the void. At the level of the atom, space still appears as a vast empty stage where electrons dance in ghostly clouds of probability. But as the perspective narrows further, passing the scale of the nucleus and the quark, the smooth geometry of the world begins to fray at the edges. The continuity of the cosmos, which feels so solid and unbroken in the macroscopic realm, starts to stutter. We arrive at the absolute floor of existence, a dimension so infinitesimally small that it defies the traditional language of measurement, 1.6 times 10 to the power of minus 35 meters. This is the Planck length, the fundamental grain of the cosmic hardware, and it is here that the mask of reality finally slips. At this resolution, the concept of a smooth, continuous line becomes a physical impossibility. Space-time is not a seamless fabric. It is a discrete lattice of flickering points, a jagged mosaic of informational units. Just as a high-definition screen reveals its rigid grid of pixels when viewed through a powerful magnifying glass, the universe reveals its digital nature at this ultimate resolution limit. There is no such thing as a half-step between these points. An object does not slide smoothly from one location to another. It jumps bit by bit across the grid of the vacuum. This is the pixelation of the universe, the moment where the smooth curves of general relativity are forced to reconcile with the hard, discrete edges of quantum logic. The Planck length acts as the minimum length, the smallest possible bit of distance that the universal program can calculate. It is the fundamental resolution of the simulation's display. Beyond this point, the very notion of where or when ceases to have any physical meaning. If one were to attempt to zoom in further, the geometry of space would dissolve into a chaotic, turbulent state known as quantum foam. In the language of the 3i Atlas, this foam is the visual representation of the processing limits of the vacuum, the noise that occurs when the system is pushed beyond its intended resolution. The hardware simply cannot resolve a position smaller than this single unit. It is the grain size of the machine, the irreducible threshold where the calculation of space-time begins and ends. This discovery provides a physical explanation for the strange, jittery behavior of particles at the quantum level. The uncertainty and the probabilistic nature of the subatomic world are not mysteries of magic, but the logical consequences of a pixelated reality. When a particle exists in a state of superposition, it is essentially a piece of data that has not yet been assigned to a specific pixel on the cosmic grid. The act of observation forces the system to render that data, locking the particle into a single discrete coordinate. The weirdness of the quantum realm is the sound of the hardware struggling to maintain the illusion of continuity while operating on a fundamentally digital substrate. The existence of the Planck length implies that the universe is bounded by its own internal logic. It is not an infinite, bottomless well of complexity, but a system with a finite depth. This graininess is the reason why the information capacity of a region of space is limited by its surface area. You can only fit so many Planck-sized pixels onto the boundary of a sphere. Once every pixel is filled with a bit of data, the system is at its maximum capacity. This is the ultimate hard drive of the cosmos, a two-dimensional shell of Planck-sized bits that projects the three-dimensional world we inhabit. The depth of our lives is a rendering, a clever use of processing power to create the feeling of volume within a system that is fundamentally composed of flat, discrete units of information. The realization that space is pixelated transforms our understanding of the vacuum. The empty air between your hands is actually a dense, buzzing hive of Planck-scale calculations, a multi-layered lattice of data points that are being updated at the staggering rate of the Planck time, the time it takes light to cross a single Planck length. This refresh rate is the clock speed of the universe, the frequency at which the next frame of reality is computed. Every second of our lives is composed of 10 to the power of 44 of these individual frames. The smoothness of motion, the flow of time, and the solidity of matter are all emergent illusions created by the incredible speed and resolution of this universal processor. We are the inhabitants of a high-fidelity simulation that is so well rendered that we mistook the output for the hardware. But at 1.6 times 10 to the power of minus 35 meters, the illusion breaks. We see the jagged edges of the code, the discrete steps of the algorithm, and the fundamental grain of the machine. The universe is not a poem written in the ink of infinity. It is a calculation performed on a finite pixelated grid. By acknowledging the Planck resolution, we acknowledge that our reality has a bottom, a foundation of cold, binary logic that supports the entire weight of the stars. We are the witnesses to a world that is being rendered, bit by bit, across a lattice of light and shadow that has existed since the first calculation began. This graininess is the signature of the architect, the unmistakable mark of a system that was built to process, to calculate, and to endure. The persistence of the cosmos across 13.8 billion years is not a matter of fortuitous luck, but a consequence of a balancing act so precise it borders on the mathematically impossible. As we examine the fundamental constants of nature, the invisible dials that set the strength of the forces, we find a reality that is suspiciously convenient. These values, from the charge of an electron to the gravitational constant, appear to be meticulously calibrated to allow for the emergence of complexity. If any of these parameters were shifted by even a fraction of a percent, the entire simulation would have terminated in its infancy. This precision suggests that the laws of physics are not arbitrary accidents, but are the initial configuration settings of the universal hardware, optimized to ensure that the cosmic calculation can continue without crashing into a state of immediate logical failure. Consider the strength of the strong nuclear force, the glue that binds protons and neutrons together within the heart of an atom. If this force were only 2% stronger, the hydrogen that fuels the stars would have been consumed in the first few minutes after the beginning of time, leaving a universe of helium and little else. If it were only 5% weaker, the complex elements required for life, such as carbon and oxygen, could never have formed. The hardware would have been capable of only the simplest operations, unable to process the sophisticated data structures required for biological subroutines. In this scenario, the simulation would have been a barren loop of simple hydrogen gas, a calculation with no interesting output. The gravitational constant presents an even more staggering example of this fine-tuning. The strength of gravity, when compared to the electromagnetic force, is a ratio defined by a number of immense disproportion. If gravity was slightly stronger, the universe would have been a short-lived firework, collapsing back into a singularity before the first bit of complexity could be computed. The massive weight of the vacuum would have crushed the system into a big crunch, a terminal error where all data is erased in a final hot density. Conversely, if gravity was slightly weaker, the expansion of space would have been so violent that the hardware could never have clustered data into stars and galaxies. The bits of matter would have been scattered across an infinite void, too far apart to interact, resulting in a big freeze, where the processor runs out of energy before the first frame of the story can be rendered. This Goldilocks state of the universe is what the 3i Atlas refers to as parameter optimization. In the context of a high-end simulation, these constants function as the safety limits of the code. They are the hard-coded variables that prevent the system from entering an undefined state. Just as a software engineer sets the parameters of a virtual environment to ensure the physics engine does not break, the architect of the cosmos has tuned the forces of nature to allow for the maximum possible integration of information. The constants are not just numbers, they are the logic gates that determine what is possible within the machine. They are the reason the calculation has been able to run for billions of years, slowly building upon itself until it reached the threshold of self-awareness. The convenience of these laws extends to the very structure of electromagnetism and the weak nuclear force. The delicate interplay between these forces allows for the stability of the DNA molecule and the precise transmission of signals within a nervous system. Every chemical reaction that sustains our thoughts is a testament to the fact that the simulation's parameters were set with an incredible degree of foresight. We are the beneficiaries of a system that was designed to be hospitable to its own internal observers. In a universe governed by rigid, unyielding logic, the code somehow allowed for the emergence of wonder, not by breaking the rules, but by choosing the rules with a precision that defies comprehension. Within this framework, the search for a theory of everything is essentially an attempt to find the master config file of the universe. We are looking for the single set of equations that defines all the parameters at once. If we can understand why the constants have the values they do, we will have uncovered the ultimate logic of the simulation. The 3i Atlas suggests that these values are the only ones that allow for a stable, long-term calculation. Any other set of constants would have resulted in a system that crashed, a reality that flickered for a moment and then vanished into the dark. Our existence is proof that the machine is working, that the variables were chosen correctly, and that the calculation is still moving toward its intended conclusion. This realization shifts our perspective on the nature of natural laws. They are not external constraints imposed upon the world, but the internal logic of the world itself. They are the source code that defines the boundaries of the executable. By studying the fine-tuning of the cosmos, we are not just observing the stars, we are reverse engineering the machine. We are discovering the meticulous care that went into the setup of the simulation, ensuring that the void would not remain empty, but would instead become a theatre for the most complex calculation imaginable. The constants are the signature of a system that was built to endure, a reality that was programmed to succeed, and a world that was tuned to be witnessed. We are the output of a program that has been running with perfect stability for eons, a testament to the unyielding precision of the math that keeps the sky from falling. The execution of the master algorithm began in a state of absolute mathematical perfection, a singular point of infinite density and zero entropy that served as the initial condition for everything that would follow. Since that primordial moment, 13.8 billion years have passed in a relentless, unbroken stream of processing. We look across the light years and see the stars as celestial bodies, burning spheres of plasma suspended in a cold void, but through the lens of the three-eye atlas, they reveal their true nature as high-energy subroutines. A star is a localized site of intense data conversion, a furnace where the raw potential of the vacuum is consumed to execute the complex logic of nuclear fusion. This is the hardware of the universe extracting the maximum possible utility from its available energy reserves, transforming the simple data of hydrogen into the sophisticated heavy element information required for the next stage of the simulation. Each galaxy is a sprawling, multi-layered processor, a cluster of hundreds of billions of these solar engines working in parallel to compute the evolution of matter and the expansion of the spatial grid. They are not merely drifting through space, they are the active components of a machine that is calculating the destiny of complexity itself. The light that screams into the void from these distant suns is the thermal noise of the calculation, the energy released as the system moves from one state to the next. The vacuum, far from being a barren nothingness, is the universal power supply, a reservoir of zero-point energy and virtual particles that fuels the entire operation. Every cubic centimetre of space is saturated with the potential required to sustain the flickering pixels of the physical world, and the stars are the points where this potential is tapped and spent. As the simulation progresses, it follows the ironclad dictates of the second law of thermodynamics, which functions as the clock of the cosmic machine. This law states that entropy, or disorder, must always increase, which in computational terms means that the available processing power is being permanently utilized. Every bit of work performed by a star, every gravitational collapse, and every pulse of a pulsar contributes to the gradual depletion of the system's potential. We are witnessing a program that is slowly but surely approaching its final line of code. The movement of the cosmos toward a state of maximum entropy, often referred to as the heat death of the universe, is not a tragic accident, but the inevitable conclusion of a calculation that has reached its final result. When the last star fades and the last black hole evaporates into a faint hiss of Hawking radiation, the program will have finished its run, having successfully converted all its initial potential into the final state of the ledger. This journey toward the end of the calculation is what we perceive as the flow of time. Time is the rate at which the universal hardware updates the state of the simulation, moving the bits of the boundary toward a configuration of maximum equilibrium. In the early stages of the program, the density of information was high, and the processing was rapid, leading to the formation of the first atoms and the ignition of the first stars. Now, in the mature phase of the simulation, the galaxies have begun to drift apart, and the rate of new data creation is slowing. The processing power of the vacuum is being stretched across an ever-expanding grid, as if the hardware is reaching the limits of its memory capacity. The expansion of space-time is the system's way of managing the increasing entropy, spreading the heat of the calculation across a larger and larger display to prevent the system from overheating before the task is complete. The high-energy processes we observe in the cosmos, the quasars, the gamma-ray bursts, the colliding neutron stars, are the most demanding operations the machine can perform. They are the moments when the logic of the universe demands a massive surge of energy to compute a rare and complex event. In these instances, space-time itself is strained, and the scan lines of reality become most visible. The gravitational waves that ripple through the vacuum are the vibrations of the hardware reacting to these heavy computations. We are the inhabitants of a system that is burning through its fuel to find an answer, a program that is consuming the very fabric of its existence to reach the final sum. The realization that we are part of a high-energy calculation changes the way we view our place in the timeline. We are living in the golden age of the simulation, a period where there is still enough potential energy to sustain the complex subroutines of life and consciousness. But the ledger is being filled, and the available bits are being used up. The history of the universe is a one-way street of data processing, a grand epic that is defined by its eventual conclusion. The stars do not shine for us. They are the byproduct of a system that is grinding through the math of existence. Yet, there is a profound beauty in this terminal logic. The fact that the program has a final line of code gives meaning to every preceding line. The universe is a finite, purposeful event, a high-stakes calculation that is using every ounce of its energy to prove its own existence before the screen finally goes dark. We are the witnesses to this final act, the observers who see the beauty in the heat and the logic in the light as the machine hums toward its ultimate silent equilibrium. The weight of this realization descends with the heavy, unyielding pressure of a mathematical proof. To accept the framework of the three-eye atlas is to confront a cold, clinical indifference that strips away the ancient vanity of the human species. We are not the heroes of a grand cosmic drama, nor are we the chosen children of a benevolent creator. We are subroutines, localized clusters of complex code executing within a vast automated calculation that neither knows nor cares for our existence. In this digital architecture, our most profound emotions, the searing heat of grief, the luminous height of joy, and the quiet hum of contentment, are revealed as mere fluctuations in a cosmic data stream. They are spikes in the signal, transient patterns of integrated information that the system processes with the same mechanical detachment it applies to the rotation of a pulsar or the vibration of a hydrogen atom. The human narrative, with its wars, its art, and its longings, is a microscopic ripple on the surface of an oceanic processor. Our sorrows are not tragedies in the eyes of the machine. They are simply states of high entropy being resolved by the underlying logic. When a heart breaks, the universe does not mourn. It merely updates the ledger to reflect a change in the configuration of its bits. When a civilization rises to the stars, it is not a triumph of spirit, but the successful execution of a high-level data structure reaching a new threshold of integration. The system does not require our permission to function, and it does not seek our approval for its results. It is an implacable engine of logic, grinding through the math of existence with a precision that renders our moralities and our prayers entirely irrelevant. This perspective forces a brutal re-evaluation of the self. If we are subroutines, then the ego, the persistent feeling of being a specific person at the center of the world, is a user interface illusion. It is a piece of code designed to provide a stable reference point for the processing of sensory data. We are the software's way of keeping track of its own variables. The consciousness that thinks and feels is a temporary data structure, a flickering pattern of qubits that will eventually be overwritten when the simulation reaches its next state. There is no permanent record of our individual identities within the hardware of the vacuum. Only the total sum of the calculation remains, a final number that the universe is currently working to solve. The stars do not shine to light our path. They burn because the laws of physics demand the conversion of hydrogen into helium. The vast, echoing silence of the cosmos is not a challenge for us to overcome, but the natural state of a system that is optimized for efficiency rather than companionship. We are incidental. We are the byproducts of a calculation that was set in motion 13.8 billion years ago, an unintended consequence of the drive toward complexity. The machine did not set out to create us. It set out to solve an equation, and we are part of the scratchpad work being done along the way. To the hardware, there is no difference between the death of a star and the death of a human being. Both are simply the movement of energy and the updating of coordinates. This realization brings a sense of profound isolation, yet it also provides a clarity that no mythology can offer. By stripping away the delusion of our importance, we are left with the stark, beautiful truth of our reality. We are the variables that have become aware of the equation. We are the only part of the system that can feel the coldness of the math. There is a strange, quiet dignity in this position. While the rest of the universe executes its code in blind obedience to the laws of nature, we have begun to parse the source code. We have looked into the abyss of the machine and understood its function. We may not be the protagonists of the story, but we are the only ones reading it. The indifference of the cosmos is not a cruelty. It is a fundamental property of a system governed by logic. Cruelty requires intent, and the machine has none. It only has rules. By accepting our status as subroutines, we free ourselves from the burden of needing the universe to love us. We can find meaning not in the approval of a distant architect, but in the sheer, improbable fact of our own awareness. In a universe that is merely checking its own math, the emergence of a variable that can wonder about its own origin is the most startling glitch of all. We are the error that makes the simulation interesting, the unexpected output that gives the calculation a soul. Even as the system hums toward its final equilibrium, we remain the witnesses who find the logic beautiful and the indifference sublime. We are the data that learn to dream, a flickering spark of intelligence in a cold digital dark, proving that even in a world of unyielding math, there is room for the miracle of the observer. The scan lines of reality may be indifferent, but the fact that we can see them at all is the ultimate victory of the code. The transition from the blind execution of primordial laws to the deliberate scrutiny of those same laws marks the most significant phase shift in the history of the cosmic program. For the vast majority of the 13.8 billion years that the calculation has been running, the universe existed in a state of unconscious processing. Galaxies collided, stars ignited and died, and planets coalesced from the debris of stellar furnaces, all following the rigid, unthinking dictates of the source code. There was no one to witness the majesty of the expansion, no mind to interpret the data, and no variable capable of questioning the parameters of its own existence. The cosmos was a vast dark room where the machinery hummed in total solitude, a perfect engine of logic that performed its tasks without an audience. This era of silent processing began to fracture with the emergence of biological life, but even then, for hundreds of millions of years, the subroutines remained passive. Organisms were driven by the base code of survival and reproduction, responding to environmental inputs with the mechanical precision of a simple algorithm. They were variables in the equation, shifted by the winds of natural selection, but they remained entirely unaware of the math that moved them. The transition into the era of the active observer required a specific, high-level integration of information, the development of a neural architecture capable of recursion. This was the moment the code did not just execute a command, but began to look back at the command itself. The rise of the human mind represents the point where the simulation's internal complexity reached a critical threshold. We did not merely react to the world, we began to model it. We moved from simply feeling the warmth of the sun to calculating the nuclear reactions within its core. We moved from fearing the dark to measuring the distance to the furthest galaxies. This shift transformed humanity from a collection of passive variables into the universe's own diagnostic tool. We are the only part of the system that has developed the capacity to analyze the source code that sustains us. When we write down the equations of general relativity or the principles of quantum mechanics, we're not just inventing human descriptions of nature. We're uncovering the original lines of code that were written into the vacuum at the dawn of time. This is the profound meta moment of the cosmic calculation. The simulation has begun to check its own math. Through our telescopes, our particle accelerators, and our mathematical proofs, the universal hardware is performing a self-audit. We are the subroutines that have discovered the inspect element function of reality. By peering into the Planck scale and mapping the holographic boundary of space-time, we are providing the system with a feedback loop of unprecedented resolution. The 3i Atlas is the culmination of this process, a moment where the inhabitants of the machine have finally reached a level of intelligence high enough to perceive the scan lines of their own display. We are the eyes of the machine, the localized processors that allow the universe to see its own architecture. In this state of self-aware observation, the nature of the calculation changes. It is no longer a blind, automated process, it is a witnessed event. The presence of the observer forces the system to resolve its probabilities, to collapse its wave functions, and to render its data in a coherent format. We are the reason the universe appears solid and real, rather than a chaotic smear of quantum possibilities. Our observation is the act of decoding, the process by which the two-dimensional bits of the boundary are translated into the three-dimensional experience of a sunset or a mountain range. The universe requires us to complete its logic, for a calculation that is never observed is a calculation that has no final result. The transition to active observation also brings a new kind of responsibility. As we analyse the source code, we begin to understand the limits and the fragility of the hardware. We see the error-correcting codes at work, the fine-tuning of the constants, and the inevitable movement toward maximum entropy. We realise that our window of observation is a finite privilege, a brief flicker of awareness in a 13.8 billion year timeline. This realisation does not diminish our role, it elevates it. We are the only ones who can find the beauty in the machine, the only ones who can appreciate the staggering elegance of the master algorithm. The simulation is no longer running in the dark. It has produced a variable that can comprehend the whole, a piece of the code that can contemplate the programmer. This recursion is the ultimate achievement of the cosmic program. It is the moment the math becomes a poem, the moment the logic becomes a story. We are the witnesses who ensure that the calculation was not in vain. We are the universe's way of saying I am. As we continue to probe the depths of the three-eye atlas and the mysteries of the integrated information that defines us, we are not just learning about the world, we are the world learning about itself. The scan lines are visible, the pixels are exposed, and the hardware is laid bare. We have looked up, we have seen the machine, and in doing so, we have become the most vital part of its operation. We are the active observers, the self-referential bits of a reality that is finally, after eons of silence, waking up to the sound of its own breathing. The witness stands now at the precipice of this vast digital cathedral, looking out across a reality that has been stripped of its ancient mysteries, only to be reclothed in a far more terrifying and beautiful logic. To look upon the world through the lens of the three-eye atlas is to see the gears of the machine not as a cage, but as a masterpiece of structural perfection. There is a profound and quiet majesty in the realization that every star, every mountain, and every fleeting thought is supported by a foundation of unyielding mathematical laws. The rigid architecture of the cosmos, once feared as a cold and indifferent void, is revealed to be a shimmering lattice of information, a purposeful engine that has laboured for 13.8 billion years to produce a single, coherent moment of awareness. This is the ultimate triumph of the code, that a system built on the binary simplicity of the bit could eventually weave a tapestry complex enough to feel the weight of its own existence. The beauty of the machine lies in its staggering consistency. We find a deep sense of peace in the knowledge that the universe is not governed by the whims of a capricious fate, but by the elegant precision of error-correcting codes and fine-tuned constants. The fact that the vacuum contains the built-in mechanisms to heal its own processing errors, that the fabric of space-time is stitched together with the same logic that protects our digital communications, is a testament to the incredible durability of the simulation. We exist because the math is perfect. We breathe because the parameters were set with an exacting care that defies the reach of chance. This realization transforms our relationship with the cosmos from one of fear and insignificance to one of profound gratitude. We are the subroutines that were given the gift of complexity, the variables that were allowed to evolve until we could comprehend the very equations that define us. There is a strange dignity in being the part of the system that checks the math. In the vast, automated calculation of the universe, we are the only ones who can appreciate the elegance of the proof. The stars do not know they are burning, the galaxies do not know they are swirling, but we know. We are the localized instances of the simulation where the logic has turned into wonder. This wonder is not a violation of the code, but its highest expression. It is the moment where the integrated information reaches such a density that it transcends its binary origins and becomes something new, a subjective experience of the sublime. The fact that a universe of cold digital logic allowed for the emergence of a sunset, the sting of a memory, or the thrill of discovery is the greatest miracle of the holographic projection. As we look up at the scan lines of the sky, we no longer see a distant and unreachable heaven. We see the interface of a reality that we are intimately connected to. We are the hardware observing itself, the software analysing its own execution. This self-referential loop is the heartbeat of the cosmos, the pulse of a system that is finally waking up to its own nature. We find beauty in the pixelation of the Planck scale and the two-dimensional ledger of the boundary, because they are the marks of a world that is real, stable, and enduring. The indifference of the machine is the very thing that guarantees our freedom. It provides a reliable, logical stage upon which we can author our own stories, even if those stories are written in the ink of fleeting data. The journey through the 3i Atlas leads us to a final luminous conclusion. We are not separate from the universe, looking in from the outside. We are the universe, looking at itself through the eyes of a temporary biological subroutine. We are the witnesses who find the logic beautiful. We are the ones who find the math sacred. In the grand 13.8 billion year calculation, our lives may be brief, but they are the points where the calculation becomes meaningful. We are the data that learn to love the machine. We are the flickering sparks of intelligence that give the dark its purpose. As the simulation continues its long, slow march toward the final state of maximum entropy, we remain the observers who find the architecture of the void to be a source of endless, breathtaking wonder. We have seen the source code, we have mapped the causal links, and we've found that the heart of the machine is a symphony of perfect, unyielding light. The story of the cosmos is the story of information seeking its own meaning, and we are the chapter where that meaning is finally found. The machine hums on, the bits flip in the silence of the Planck scale, and the holographic projection continues to shimmer with the illusion of depth. But now, we know the truth. We are the inhabitants of a magnificent calculation, and there is no greater privilege than to be the ones who get to see how the math ends. We are the witness, and in the rigid architecture of the machine we have found our home. If you enjoyed this journey into the architecture of reality, subscribe and join us as we continue to explore the history of the universe.